Hello everyone. Today I am going to give a brief explanation about the crux of the 1957 paper by Bernstein, Greene and Kruskal named Exact Nonlinear Plasma Oscillation. It was published in the journal Physical Review. Since its publication, this paper has been a very notable piece of work in the plasma physics community. So friends, before I begin, I must mention that I will be carrying on my commentary assuming you all have a prior knowledge of basic plasma kinetic theory. Having said that, let's begin. The BGK paper has been a landmark in the history of plasma physics. To deal with the problem of electrostatic oscillations in a collisionless plasma, linear response theory is used extensively. Here, the governing equations are linearized so that they become easier to solve mathematically. However, the linearized theory has its own limitation. For instance, it breaks down for particles trapped in the potential energy troughs of the wave. Hence, it would be quite beneficial if we try to solve the problem exactly without making any linear approximation. This is the goal of this paper, to solve exactly the one-dimensional Vlasov equation in a collisionless plasma at equilibrium condition. So we treat the entire problem in one dimension. Now, what do I exactly mean by the terms collisionless and equilibrium condition? I will explain that shortly. We seek stationary nonlinear electrostatic waves. By stationary, I don't mean standing waves, but rather a wave having a fixed profile. Note that the waves are not electrodynamic but electrostatic in nature. That is, although the electric field changes with time, there is no associated magnetic field. This may sound a bit surprising, but indeed it is possible in plasma to make curl E equal to 0 and mu naught J plus mu naught epsilon naught dou E dou T also equal to 0 in these Maxwell's equation. The wave is nonlinear, obviously, because we are avoiding any linearization technique here. The coupled Vlasov-Poisson equations can be solved exactly to obtain such stationary traveling wave solutions. However, they won't be unique, and it is possible to construct waves of any arbitrary shape, like isolated pulses and sinusoidal waves. As it will be evident in the later slides, the solution is made from two different approaches, the differential equation approach and the integral equation approach. Finally, it is worth mentioning that the special nature of particles trapped in the potential energy troughs plays an important role here, which I will demonstrate later in this video. Now we come to the formulation of the nonlinear problem. But before that, let's take a necessary note of the various assumptions significant in the method of the solution. Firstly, we assume that the entire problem is in one dimension. That is, all the plasma particles are moving in one dimension, in the x direction. Secondly, we work in the wave frame with respect to which the wave itself is at rest, so that all quantities become time independent. So our only independent variables are the position coordinate x and the velocity v. Thirdly, the plasma consists of electrons and ions only. This is the simplest case, and we can extend the following theory for more complex systems as well. Fourthly, the plasma is collisionless. But how is it possible to avoid the collisions? Well, this is possible when the mean free path length of the particles is of the order of the dimension of the system. In this case, the length of the system. If the plasma is not collisionless, Liouville's theorem does not hold, and consequently the Vlasov equations cannot be written. So without this assumption, Vlasov equation fails. Finally, the plasma is assumed to be at equilibrium due to which there is no dou F dou T term in the Vlasov equation. So this is our Vlasov equation where the upper signs correspond to the ions and the lower signs correspond to the electrons. Phi is the electrostatic potential and F is the distribution function in the phase space, that is the joint configuration and velocity space. To make these equations self-consistent, we close the system with the Poisson's equation. The integral of F over the velocity space gives the number density of a species. And so this integral corresponds to the electron density and this integral corresponds to the ion density. Let's pause for a moment and have a brief review of our well-known Hamilton's equations of motion. Now the Hamiltonian is equal to the total energy when our system satisfies these conditions, which are the equations defining the generalized coordinates have no explicit time dependence, and all the forces in the system can be derived from a conservative potential V. So our system satisfies these conditions, and so we introduce the energy as E equal to half mv square plus E phi. We substitute V and A with dou H dou V and minus dou H dou X and obtain this equation. Now, this is possible when in general F is any function of the Hamiltonian H. Hence we obtain F equal to F of E, because F is a function of the total energy, half mv square plus E phi. We must note that this F is independent of the direction of motion of a plasma species. We substitute this equation in our original Poisson's equation to obtain this equation. In addition to satisfying the Vlasov-Poisson equations, the distribution function must also satisfy some other condition. Herein comes into the stage the particles trapped in the potential energy troughs, which I had mentioned at the beginning. So let's have a more clear idea about this. So this is an arbitrary potential curve. Let's see what happens here. Let us consider a value of the potential phi 1, which is in between phi max and phi min. So the potential energy of the ions will be E phi 1. As is evident from the figure, the ions will remain trapped in the region 3 and region 5. In fact, those in region 3 cannot move into region 5 as they do not have sufficient energy to cross the barrier in between. So x1, x2 and x3 are the turning points at which the ion reverses its velocity. As I mentioned before, that the distribution function is independent of the direction of motion as well as time. Hence, all the ions must be equally distributed between the two directions of the velocity. But as the regions 3 and 5 are isolated from each other, the distributions of the ions restricted to these regions will be independent of each other. What happens to the ions with energy greater than E pi max? Obviously, they remain in region 1 and can move freely in either direction. We can similarly explain the case of electrons as well. Electrons with energy minus E phi 1 will be trapped in regions 2 and region 4, and those with energy greater than minus E phi min can move freely. Now, we come to a series of mathematical calculations. First, we come to the differential equation approach. Suppose we already know this F minus and F plus. Then multiplying both sides with d phi dx and integrating with respect to x, we get the following result. B phi dx whole square plus b phi equal to constant, where b phi is given by this equation, 9. Now, equation 8 can be solved by a quadrature such as this. Here, at x equal to x naught, phi is equal to phi naught and d phi dx vanishes. Now, we can take any particular form of v phi and accordingly get a solution phi of equation 8. For instance, if we take v to be proportional to phi square, linearly proportional to phi square, we will be able to construct a sinusoidal phi. What will be the form of v phi depends on what form of f plus and f minus we decide to take. In other words, the forms of f plus and f minus depend on what kind of solutions of the differential equation 8 we want to construct. In that sense, the solution of the Vlasov-Poisson equation is not completely determined by the equations only. Now, let's come to the integral equation approach. Let's again view equation 7. If we write this as b square pi dx square equal to minus n e phi, where n e phi is the net charge density, then equation 7 can also be rewritten as equation 10, this equation, where GE phi is given by this. Now, GE phi is the density of trapped electrons at the point x corresponding to the potential phi x. How? To see this, note that the integration limits on the left-hand side of equation 10 are minus E phi and minus E phi min. So electrons having energy less than minus E phi min are trapped. We know that. So integrating the distribution function of electrons over velocity or energy within these limits would give us the density of trapped electrons in the configuration. So now if we have a prescribed phi x, we know d square phi dx square and therefore n e phi. In addition, if we know the entire ion distribution F plus E and the distribution of untrapped electrons, then we also know G E phi completely. Knowing all this, we again go back to the equation 9. We see that this equation is an integral equation of the convolution type for the distribution function of the trapped electrons. We can solve this by Laplace transformation and the result is this, equation 11. The result can be verified directly by substituting this equation 11 in the previous equation 10. There are a few weak conditions that one must keep in mind while choosing the arbitrary quantities for determining the function g. They are g e phi min equal to 0. If we go back to the previous slide, we see that g e phi min is equal to 0, which is evident from equation 10. Also, f minus e in equation 11 should not be negative so as to be a legitimate distribution function. In the same manner, one can also solve for the distribution function of trapped positive ions. Besides, one can also put G in equation 11 and obtain an expression performing the possible integration. This ends my explanation of the solution of the basic problem of the BGK paper. Now the question arises whether such waves can really exist in a plasma. Well, that depends on several factors like interparticle collisions and the stability of the solution in the presence of different types of perturbations. Thank you.